Scalar fields are ubiquitous in scientific visualization. To apprehend the complexity of such datasets, several topological techniques have been proposed to capture the structure of the field into high-level topological abstractions, such as a rig graph in this example. Moreover, efficient methods exist to simplify these abstractions, hence enabling multi-resolution representations of the topology of the field. However, these algorithms don't actually simplify the underlying scalar field. In many application scenarios, having a simplified version of the field can be useful for visualization or geometrical analysis. Sometimes, one can even desire to obtain a simplified scalar field without having to compute a topological abstraction beforehand, which can be computationally expensive. In this work, we present a general approach to scalar field simplification on surfaces. Our technique is combinatorial, thus, it is not sensitive to numerical instabilities as found with existing numerical techniques. In contrast to previous combinatorial approaches, our algorithm works directly on piecewise linear scalar field representations, which is more acceptable application-wise. Also, it handles surfaces with or without boundary, and is robust to multiple saddles. Finally, it addresses a more general problem, for which traditional epsilon-simplification is shown to be a special case. Thus, it enables to remove critical points arbitrarily, as showcased in this example, where the user interactively removes singularities. Since it does not compute any expensive data structure, such as a Morse-Mel complex, a contour tree, or even a union find, our algorithm is extremely fast in practice, even in worst-case scenario approximations. In the special case where persistence is used as a feature selection strategy, our algorithm produces a standard epsilon-simplification, which means that all the remaining critical points are more persistent than a threshold epsilon, and that the maximum norm between the input and the output is at most epsilon. Moreover, our algorithm locks the remaining critical points both in terms of function value and in terms of location. We apply our algorithm to Turing simplification, where we show that ad hoc feature identification strategies can drive a robust topological simplification algorithm. The Grand Canyon can be decomposed from a geographical point of view in three main regions: the canyon itself, its north rim, and its south rim. By enforcing the suppression of all the singularities inside the canyon, our algorithm emphasizes the topological features on the rims only. On the contrary, we can emphasize all the peaks in the canyon. For comparison, an epsilon simplification with compatible maximum norm completely removes the features irrespectively of their location, and yielding a worse average data fitting. Many geometry processing problems involve numerically sensitive tasks. In many cases, the topology of the numerical solution is of first importance. In this example, we consider the Laplace equation with Dirichlet conditions. Several discretizations exist for the Laplace operator. The combinatorial Laplacian is robust from a topological point of view, since the only extrema in the solution indeed correspond to the Dirichlet constraints. However, it provides poor geometrical accuracy, yielding artifacts on the level lines. In contrast, the discretization based on cotangent weights provides a much better approximation with much smoother level lines. However, it is sensible to the presence of sharp triangles in the mesh, and it can generate additional critical points which prevents the solution from conforming to its formal description. Our algorithm can be used in a straightforward manner, without any threshold parameter, to automatically remove this numerical noise. Hence, it provides a solution both benefiting from the topological robustness of the combinatorial Laplacian, and from the geometrical accuracy of the cotangent weight Laplacian. Hence, it enables to design scalar fields with topological guarantees for certified geometry processing.